Swayam Prabha. Digital India. Educated India.
So far we have talked about various types of materials, but in this last series we will enter into the application of this knowledge domain. That means, now we are going to talk about how all this knowledge that you have acquired so far, on the basis of that knowledge, how you can basically select a particular material for some engineering design applications. So, there will be various case studies that we will carry out, and this will be really the test of how much knowledge you have acquired towards the material properties. So, what we are going to talk about, for example, is the general. Today we will discuss all these things in principle, and from the next class we will talk about that how to apply it. So, today we are going to talk about the general aspects of the mechanical design, design flow chart, and the doubling time issues, resource availability, eco-efficiency, and finally, the SB chart. The knowledge of SB chart, which is the culmination of today's lecture, is very, very important for us to apply from the next lecture onwards. So, let us first talk about that what do we mean by mechanical design, because I said that we are going to talk about material selection for mechanical design. Now, mechanical design refers to the mechanical component design which has definitely some mass and which will carry some load, that means it is functional, and also it may have other functionalities such as thermal or electromagnetic requirements, and then it must be manufactured. So, that is the that is the way this kind of design would qualify. And the design per se would refer to the selection of engineering materials based on a set of defined properties. So, it will be naturally an iterative process. What we will try to do is that corresponding to some functional requirement, let us say you have functional requirement A. So, you have a particular functional requirement, let us say, then corresponding to this requirement we will say F1 is the functional requirement. We will try to find out that what is the performance index that we should look for, and this performance index we should look for from the material property point of view. So, this will be from the material property point of view, and then we will go through all our knowledge of the materials, and we will see that which group of materials can give you the best performance index, that means can satisfy this function in the very best manner. So, that is what is the essence of the whole direction. Now, in any particular design, when we do, what exactly we actually carry out in this design process. So, we first start with the market need. What are the design requirements in a market? Let us say tomorrow I want to develop, I find out that there is a energy crisis. So, there is a market need of developing a micro scale energy solution. Then we have to find out what is the design requirement. Do I need to actually design a system which can extract energy from say wind energy or from water, or maybe from both, or from vibration. So, we have to find out what are the design requirements. Based on that, we have to go for a conceptual solution. So, at this stage we have to determine what is the function structure, that means how many functions this particular concept has to satisfy, and then we have to seek what are the working principles corresponding to this function structure, and we have to select, evaluate and select the concepts, because you can have multiple concepts, right. So, one can give many design concepts, say C1, C2, C3. So, each concept you have to find out that in a something called PU chart, okay, you have to find out that which concept is good for a particular work and which concept is not so good. So, once we rank this concept, then we choose one concept from that and then we go ahead with the next part, which is known as the embodiment design. In the embodiment design part, we actually develop the layout, scale, forms, etc. And then we also work on the system model, we analyze the system and then we evaluate and select the layout. So, embodiment design is something like a detailed analysis that you have to carry out in order to know that what sort of material system you will need in terms of materializing the concept. Then you have to come to the detail, and in the detail part we are going to talk about each of the sub assemblies, look into it in details, then optimize the performance, minimize the cost and then choose the final set of material and the process. So, when we are at the conceptual stage, generally we do not select the material, but at the embodiment stage we have many candidate materials. So, at this stage we have many candidate materials, and when we are doing the detailed design, here we finalize the material selection. And then we see that how the product specifications are satisfied and we can iterate that process. Okay. Suppose we are not happy with it, we may go back to the concepts, we may look into the other concepts, like we can then work with concept 2 or concept 3 and then carry out the same process again and again until and unless we are satisfied with the solution of the system. Now, when we will be selecting a particular material for a particular function, what are the points that you have to keep in your mind? The first important point you have to keep in your mind is the money, that is the price and availability of the material. So, that is the first important part we have to keep in our mind. Then the second is we have to look into the group of mechanical properties. And in this group of mechanical properties, we have to think of things like density of the material, because many times your system is to be of lightweight. Then you have to think of the modulus, because modulus is related to stiffness of the system. We will see it through some example in the next class. We may have to think of the damping, because for dynamic works damping is very important. Then the yield strength, the tensile strength, the hardness, fracture toughness, fatigue strength, the thermal fatigue resistance, particularly if it is for a high temperature application, as well as the creep strength. So, these are like certain very important mechanical properties. Other than that, there could be some more properties very specific to the application, but these are definitely some of the very important mechanical properties that we need to look into before we select a particular material. Next, we are going to talk about the other properties like thermal, like optical, magnetic and electrical properties. This comes because a machine, for example, today is usually multifunctional and it has to interact with a very complex environment. So, you need to know about properties which are other than the so called mechanical properties of the system. Thermal property is one of the example for example, these gas turbine blades, it has to work in a high temperature environment. So, you have to look into the conductivity of the material. So, thermal property comes into a very important property. There are some applications where the for example, a kind of a transparent oven, say if I have to design, then I have to think of that the optical property should not be sacrificed with respect to temperature. So, then that also comes into the picture, or let us say you have to design a microscope, then the optical property comes into the picture. Magnetic and electric property comes into picture. For example, I mean just some simple example that you have to design a motor housing. Now, the magnetic and the electrical properties of the motor becomes important for you. So, thus for even for mechanical design, all these things actually gets coupled, and this becomes important for us. Next is there is chemical environment change. So, the oxidation, corrosion becomes important. There could be things like friction in the system. So, the frictional properties are important. There could be abrasion or wear and tear. So, these properties becomes important for us. Now, that is the property number set number 4 that we have to look into it. Then in the property set number 5, we have to look for the ease of the manufacturing and the joining. So, this is related to the manufacturability of the system. So, design for manufacturing, and then finally, we have to think of the appearance, we have to think of the texture, feel, etc. So, the aesthetics becomes important, right. Aesthetics becomes important. So, thus this 6 property set becomes important for us. Now, once we know that these are the property sets, then we have to start to look into that what are the specific property level for each of the property set. For example, price and availability are the first important property set I told you. So, if you look into the relative prices of a system, you would see that diamond, platinum, gold, silver, these are all very expensive, right. So, till this point we are at the very expensive level of the property set. So, naturally you cannot use them unless you have a very compelling situation of using such material. So, the next interesting material which can be used is actually carbon fiber reinforced plastic. It is highly functional. I have told you when we have discussed about carbon fibers that some of the very high performance systems are designed using carbon fibers. So, this we can use, and then further, for example, tungsten is one of the material for many space grade applications. You will see that the tungsten is used. Okay. Then there will be titanium alloys once again for space grade applications, and then polyamides. Polyamides are like Kevlons, if you remember, we have talked about Kevlars, right, for bulletproof jackets. So, this is like polyamides, and then once again magnesium alloys, then nylons, polycarbonate. So, where are we in terms of for example, steel? So, steel is one of the cheapest material. So, if you look into this list, for example, you will see that the presence of steel or such material, let us say here we have the aluminum alloys in this list. Okay. Even below the aluminum alloys you can get epoxies, polyesters and glasses. That means you can make GFRPs, glass fiber reinforced plastics, and then down this line, in fact somewhere below this, because it is not here covered, I can see that the steel would come into picture. So, this is one of the cheapest material basically. Yeah, it is somewhere here, as you can see that this is where is the steel. So, you can use also that as a baseline of your material selection. Let us say if steel is 100 units of in any units, in this particular units it could be in terms of basically pound or dollar. So, however, if it is 100 units, in comparison to that, if you look at the aluminum alloys, then this is somewhere around 650 units. So, that means it is that many times expensive aluminum as a material. So, you have to be cautious of that what is going to be the cost of the system as you are trying to improve the performances using a better material. And similarly, from aluminum, let us say if you want to jump to something like magnesium alloys, this is about 1000 units. So, this is 10 times more expensive than steel. If you want to go for something like tungsten or super alloys, 5000. So, it is like 50 times more expensive. If you want to go for something like CFRPs, then it is 20,000. So, that means this is 200 times more expensive than steel. This is very important for us, because we will indeed save lot of weight by using carbon more expensive than steel, by using carbon fiber reinforced plastic, but we have to be ready to spend a 200 times more money for that system. Now, let us look into the availability of the materials. There are two groups of it, that is availability in the earth's crust and availability in oceans and in atmosphere. Of course, atmospheres you get mostly gaseous substances, but in the ocean there are certain things which are very peculiar. For example, magnesium, good supply from the ocean comes. Okay? So, that is also used as one of the structural materials. However, most of the materials that we use, they actually come from the earth's crust itself, and in terms of abundance you can see that aluminum is about 8%. So, aluminum is highly abundant. Next to that is in fact steel, but aluminum's processing cost is more, that is why aluminum is actually more expensive than steel. So, this actually gives us a broad picture of what is the abundance of different materials. Now, once you know the abundance, there is a particular knowledge which is very important at this stage, that is known as the doubling time. So, what is the doubling time? The definition of doubling time is that it is the period of time required for a quantity to double in size or value. That means, if you think of it that this is like x axis is time and y axis is the demand of a particular material, and let us say that the demand is increasing exponentially. So, if it is increasing exponentially, then at a particular time t1, if the demand is d1, how much of time would it take say t2 to go to d2, where d2 is actually twice of d1. So, that timing that is needed between this t1 to t2, that is what is the doubling time that is needed. Now, if you assume a exponential growth, in many cases the growth rate will be given to you, and hence by knowing the growth rate and logarithmic base of with respect to 2, you can actually approximately find out the doubling time to be about 70 over r. So, that means if I know the growth rate, then I can find out that what is the doubling time, and if I know the doubling time, then I know that a particular material is of very high demand, which means as I will be designing, I have to be get ready of a situation where its cost may increase because its doubling time is small. So, a material whose doubling time is more essentially is either a cheaper material, or that material is completely rare. So, either of the two cases, but the doubling time helps you to take a decision on that. Now, this also in terms of the availability, this also brings us to the very famous McKelvey diagram. Okay. So, what this diagram tells us is that this is like engineering materials, this Ashby and Jones book, you can use it for your reference for this particular beautiful diagram, that this actually tells us that there are two things, one is called reserve and the other one is actually the total resource space. So, you can have actually a very big resource space like this, okay, but a good part of this resource base may be actually undiscovered or may be actually not economic. So, it is the economy level and the level of discover known part actually makes the reserve, and rest of the things is your resource base, which includes the reserve of course. Okay. So, for example, if you consider aluminum, another point here it is important that why some of the things are not economic. Like if you consider aluminum, it takes about 280 gigajoule per ton, plastics 85 to 180 gigajoule per ton. So, these are all high energy consuming, copper 140. So, even if you find it may not be economically feasible to use such a material. So, hence your even though you have the resource, you may not be able to consider it as your reserve, because it is not profitable at that particular point of time. Now, some broad pictures I want to tell you. For example, copper, silver, tungsten, tin and mercury, they are rarely available. So, you should avoid them by all means from your general design. Iron and aluminum are most widely available material. So, you should try to use them more. Steel consumption is doubling in every 20 years. So, it is taking time and it is cheaper. Aluminum consumption on the other hand is doubling in every 9 years. So, it is going at a even faster rate, and polymers in every 4 years. So, you have to be cautious of this particular fact that at this point of time polymer is the most popular material, is have highest demand, next is aluminum and next is steel. So, accordingly you should select the material. How to encounter shortages of materials? Well, first of all you have to go for a material efficient design, that means use less amount of material. For example, for a good surface property use cheap substrate and good surface finish. Okay. So, you have to have certain tricks of using more material efficient designs. Substitution, substitute rarer materials by the more available ones. For example, substitute copper by aluminum. In the electrical wires we have seen that this has already taken place. Recycling, use such materials which are recyclable material like aluminum. This has also been done today. So, these are certain strategies that you want to take in order to encounter the shortages of materials. Next is a very important point which is known as eco-efficiency. Today we are very much conscious about the nature around us. Okay. So, it is the eco-efficiency, which means a merging of ecological and economic goals together we have to think before selecting a particular material. So, we have to think of improving the productivity of energy and material inputs to reduce the resource consumption, also cut the pollution per unit of output. Okay. So, we have to not only think of reducing my own cost, but also have to think of it that it should not affect the nature. So, a win-win approach in this direction would benefit both the bottom line design and the environment itself. Just one example, in 1989 Procter and Gamble, they introduced a concentrated detergent powder, okay, which is also called ultra detergents. They took up half the volume of traditional detergents. These products cleaned the same amount of clothes, but were more convenient for consumers to handle, use 30% fewer raw materials, required 30% less packaging and substantially cut the energy needed to transport them. So, as a result this material was actually much more eco-efficient material. There are 7 dimensions of eco-efficiency. One is to reduce the material intensity of goods and services, then reduce the energy intensity of goods and services, then reduce the toxic dispersion, enhance the material recyclability, all are very simple. So, I am not explaining them. Maximize sustainable use of renewable sources, extend the product durability, increase the service intensity of goods and services. That means increase the kind of life of the material. So, greater the improvement in each or any of these dimension, it is considered that your system is more eco-efficient in terms of a product design. So, that means you see you are not only thinking of the material to serve the particular function, but also you are thinking what is the outcome of the use of that material to the environment around us. So, that is what forces us to look into these 7 dimensions. Okay. Now, we have talked about the 7 dimensions. Finally, you have to select the material property. To do that, a fantastic chart I will introduce you tomorrow is called ASP chart. So, in this chart what you will get is that you will get this is like you can develop a n dimensional picture out of it, but in each one of the dimension you will get a comparison between suppose 2 properties, Young's modulus and strength, or suppose density and something like Young's modulus, okay, Young's modulus versus density, or say density versus some other property of the system like strength of the system, strength density. So, you can by looking at these comparison charts, let us say if I consider one of these slice of these charts here, like this is strength versus density. So, this is density and this is the strength. So, if I look at it, then I will see that the very low density materials are like foams, then from there we are going to natural materials, then from there we are going to polymers, composites. So, gradually as I am increasing the density, the strength is also increasing, okay, and then the ceramics. However, the problem is that if if I have to go for too much of high density, then the structure may be very heavy in weight. So, if I want to go for low density relatively, but high strength, then you choose something like CFRPs, because the metals are so this is where it is, but the metals at the same strength level, if you look at it, that they are actually an order of magnitude higher at the same strength level. So, that is why these 2D charts actually help us a lot in terms of selecting the material from a particular function point of view. These functions also you can plot on the SB chart, like somewhere suppose if it is sigma f by rho, that is what is your point. Then any material if it is here, it is discarded, because that is what is your functional chart level. Okay. You are searching for properties on that line beyond this level, not below this level. So, thus it helps us in terms of the choice of the materials. So, this we are going to discuss in the next class. I am going to talk about how to use SB chart, and I am going to talk about the numerical problems on material selection. Thank you.